This is an inventory management problem. It is very practical. A computer services firm regularly uses many cartons of computer paper. They purchase cartons in quantity from a discount supplier in another city that's got a cost of $22.46 per carton. Those cartons are then stored in a rented warehouse. It's used gradually as needed. There's some confusion among company managers as to how often and in what quantity the paper should be ordered. Those are real key. How often? A couple times a week, once a month, once every 4 months, once a year. And in what quantity? How many cartons of paper? 50, 100, 1,000 should be ordered. Because there are competing arguments for how often you should order. And this is very, very practical. This comes up in real life. On the one hand, since the supplier is providing out-of-town delivery by truck, there's a basic $360 charge for every order, regardless of the number of cartons purchased. It's just a delivery charge. Actually, in real life, it's probably more practical to say that charge can still go up the more you order, because it's not only the cost of bringing the cartons in the truck, that would be gas cost and vehicle wear and tear costs, but there'd also be the fact that if you got more cartons delivered, it's going to take longer to unload them, and that's going to have a labor cost to it. So we're keeping things simple, and by saying it's $360 every order, regardless of the number of cartons purchased, assuming that no orders for more than 3,000 cartons, which is the truck's capacity. I won't bother underlining that because that ends up being not super relevant to have to think about. We could, but let's not worry about that for the moment. This order cost, I'll keep this underlining green, has been used by some manager as an argument for placing large orders as infrequently as possible. Maybe 1,000 cartons just once a year or something. Just throwing out hypotheticals. We haven't looked at data about paper usage yet. That is to come. On the other hand, do this in red. On the other hand, as other managers have argued, large orders lead to large warehouse inventories and associated costs for at least two kinds. This kind of cost is a little harder to wrap your mind around. It's easy to think about delivery costs, right? You order something on Amazon, maybe you don't get free delivery, you have to pay for it. That's kind of easy to think about. But when you place large orders and you have to store the paper, there are two other kinds of costs at least. First, they claim that whatever money is used to pay for the paper, the large orders, that won't do anything. They're only going to sit in the warehouse for a long time. Paper's not being used. Could it instead, for a while at least, be allocated to some profit-producing activity? At the very least, such money could be accumulating interest in a bank account, though, of course, banks don't offer very much interest these days, though there are some online options that are offering like 3 or 4% now. It's been going up past year here in 2023. I had a bank account back in the early 80s, a savings account, where I got 8% interest at a bank. Astonishing. Inflation was even worse back then. So it wasn't necessarily keeping up with inflation back in the early 80s is what I'm talking about. But I did have a savings account that got 8% interest, and I thought that was normal. Yeah, not so much recently, but yes, they have been going up recently. This loss of investment opportunity and associated earnings is referred to as opportunity cost, resulting from the investment in paper inventory, the fact that you've had to pay a good chunk of money for a large order, and the paper is just sitting there. Opportunity cost is a real thing. You could be using a large part of that chunk of money, at least to earn interest. Secondly, the company has to pay a rent for the warehouse. Maybe they don't own the warehouse, but they got to pay rent. Does that paper sitting there in the warehouse contribute toward rent costs? You should make an argument that yes, it does, because if the paper wasn't sitting there, something else could be sitting there, some machine or some computer system or some servers or whatever, earning money in some other way. You could maybe say that's partially opportunity cost too. Anyway, it should be part of the rent. Yes, while other company property is stored there as well, the managers agree that a fraction of the rent equal to the fraction of the warehouse space occupied should be viewed as a part of the cost of storing paper. These latter two costs collectively referred to as inventory holding cost. So it sounds like they're saying lump the opportunity cost and the rental cost together and call it holding cost. It's estimated to be 18 cents per carton per week. How'd they get that? Maybe before you've come to consult with them, they've figured that out. How would they figure it out? That would depend on the details of the business. It would depend on what their rent is, how much square footage they have for their warehouse, and that kind of thing. Ultimately, these holding costs have been used to justify claims that paper orders should be smaller and placed more frequently. Instead of 1,000 cartons once a year, maybe you order 20 cartons every week. Or 5 cartons every day. Then you don't really have to store them. But it sounds bad to be too extreme, right? 5 cartons every day. They're going to be making deliveries every day. You got those big delivery costs every day. That doesn't sound so good. Probably in reality, the best choice is somewhere in the middle ground. Not large orders too infrequently or small orders too frequently, but somewhere in between. Your job, our job together here in working through this project, this inventory management project, is to decide what is that best middle ground. How big should the order be and how often should you order? Make sense? Now, before we go on, a real important point here for what we do on Friday and next Monday, and it's probably especially next Monday, is to realize that these numbers, the $22.46 per carton, the $360 charge for every order, and the 18 cents per carton per week, those are all numbers that are, well, they could change as different conditions change. The carton shot cost could change. They could raise the price. The delivery cost could change. They could raise the price. The holding cost could change based on different rental conditions, different labor conditions, lots of different things. So what in fact would be most practical is not just solving the problem at hand with these particular numbers, but better solve it no matter what numbers you got in those spots. That would be most interesting and useful. And not only could you plug in those particular numbers, but you could also ask, how does your answer for the minimum cost, we're going to minimize the cost, decide on the number of cartons per order and how often to order to minimize the cost. How does your answer depend on those numbers that I've circled? And how sensitive is the answer to them, to changes in them? That's calculus. In fact, it's going to be multivariable calculus. We're going to use multivariable calculus. Ultimately, not today, Probably not even Friday, but maybe next Monday. All right, keep going here. After talking more with various company personnel, asking many questions and inspecting company records, you've accumulated the following summary notes. Use them along with additional modeling and analysis as a basis for a report to managers recommending what quantity and how often paper should be ordered, just as I said. Okay, when I have given this as a written report kind of project in the past, people have had to write a report. Note 1, data. Company data on the number of cartons used per week is shown in this table here. No one seems to think the usage rate will change in any significant way. And yeah, look at those numbers there, how many cartons are used every week for the past year. It's very consistent, very close to 150 cartons per week. That's really actually not very realistic. But it does keep the modeling simpler. We'll use this data as justification for saying, we're going to assume we use 150 cartons for every week. So if we were ordering once a week, I guess we'd want to order 150 cartons for every order. If we were ordering once every 2 weeks, yes, we'd want to order 300 cartons per order, right? 150 times 2. So we can use them for 2 weeks. That kind of idea. Next page, note number 2. We should not let paper supply run out. Work stoppage would be disastrous. There's a best local price. If we have to order from a local supplier, maybe with a smaller delivery charge, though a higher cost per carton. I'm not going to bother underlining that because I think for the most part in our modeling, we're not going to worry about that. Discount supplier is very reliable. When an order is placed in the morning, she has never failed to deliver before 5 p.m. the next day. It seems safe to count on this. So for modeling, in modeling for simplicity, this is a very important point. In mathematical modeling, including in science, if you're going to get anywhere, you have to think as simple as possible. As simple as possible, yet still somewhat realistic. Of course, you want it to be realistic so that it accurately reflects reality. Can I say that? Accurately reflects reality. But if it's too complicated, then it's just too hard. So you want to keep things simple. That's why, for example, when you initially learn about molecules in chemistry, and including when you think about organic chemistry, you're thinking of molecules as being like Tinker Toy kind of things, right? With balls for the atoms that are connected together with bonds that are like rigid things, so that you can visualize them. Is that what the way molecules really are? Not really, right? Molecules, even atoms, are kind of, you got your nucleus with the protons and the neutrons, and you got your electrons. But what are those things? I mean, we call them particles, but are they really particles? Are they like billiard balls? No, they're not. In fact, electrons, when you get into it more deeply, are like clouds of probability. That's like quantum mechanics. To get more accurate, you have to think more deeply about these things. You have to model them more accurately with more complicated math. But when you're initially doing chemistry, you keep it simple. It's easy to visualize, and it's good enough for most purposes in a chemistry class. So we assume that the new order arrives just as the last of the stored carton is used, right? As you use it, here comes the new delivery. That's called just-in-time delivery. Of course, you really don't want to cut it quite so close, but for the purposes of modeling, as simply as possible, make that assumption. Managers seem to agree that the goal in deciding how much and how often to order should be to minimize, there's the word minimize, average weekly cost associated both with the purchase and storage of paper It's got three constituents. Again, the purchase cost. That's based on cost per carton, the delivery cost, based on the delivery cost itself, yeah. And holding cost, that was the opportunity cost and also the rental cost. When pushed to be more precise about holding costs, they say, as said on the previous page, 18 cents per carton per week, times the average inventory between orders. Note 5, it'll probably simplify modeling and analysis to assume the inventory level and time are continuous rather than discrete. So we can use calculus, that's why. Of course, nobody's going to have pi boxes of paper or pay pi dollars. But for simplicity, so we can use calculus, assume we're dealing with continuous quantities. We are in calculus, which is continuous math, as opposed to discrete math, which is not continuous math. We have a class called discrete math. It's very useful, very important, but it's not calculus. Assume your inventory level varies in a linear way, piecewise linear, going down as straight lines. When it reaches 0, then it goes back up, it jumps back up to the maximum inventory level, because that's where delivery happens. Delivery happens at these spots where you have these jump discontinuities. Now there's vertical lines being drawn in this picture, but you should realize those vertical lines are not really part of the graph, right? Because otherwise we'd fail the vertical line test. They're not really part of the graph function, but it is kind of just nice to draw them in there anyway. So now we read through it. Let's start the modeling process today, and then we'll stop for today. And this is the part you can start taking notes on. Let's focus on note 4 here. To start to come up with some kind of function giving us the cost. The function that we're going to minimize. Before we write down the function, we should probably write down some variables. That is actually the first thing you typically want to do in modeling, is write down variables. C would be a natural letter to use for cost. This is the, well, to be more technical about it, the average weekly cost associated both with the purchase and storage of paper. You could call the units dollars. You could also think of the units as dollars per week. Will it be more natural to think about one or the other? I'm going to write both here initially. I'm not sure which one's going to be more natural. Dollars, or maybe dollars per week. If we just use dollars for the units, it would be understood to be dollars per week. So in reality, dollars per week is probably the best one. But if it sort of is simpler to imagine this as a dollar amount, we just got to remember it's the number of dollars every week. How about using the letter N for, maybe the number of cartons per order. Number of cartons per order. Now again, in reality, excuse me, N would be a discrete variable. You're not going to order 117.43 cartons. You're not going to order pi cartons. But for simplicity, we'll assume N is continuous, that we could order 117.43 cartons or whatever I said, for the sake of using calculus. Maybe we use capital T for the number of weeks between orders. It's natural to use time units of weeks. Why do you use a capital letter there, a lowercase letter there, and a capital letter there? Because I felt like it, I guess. Are there any other variables? How about the average inventory between orders? Inventory level. Maybe call it I. Since it's an average inventory, maybe we even want to call it I bar. If you've taken statistics, you know a bar means average. I mean, C is an average too, so I could call that C bar. Maybe I won't bother putting a bar above it. Average inventory between orders. Let's end part one of this project analysis now by seeing if we can come up with the function we want to optimize. And then on Friday, we'll actually optimize it. C equals, I guess this is a multivariable calculus function. F of n comma t comma I. 3 independent variables. How would you visualize such a function? What would its graph look like? When you have 2 independent variables, the graph, with Mathematica, we use plot3D to see the graph was a 2-dimensional surface sitting inside 3-dimensional space. Or we can make a contour map, a 2-dimensional picture showing the level curves of the function. If you got 3 independent variables, though, whoa, 4 variables ultimately, yeah, the graph would be a 3-dimensional hypersurface sitting inside 4-dimensional space. And yes, you heard me right. I did say hypersurface. Can anybody visualize such a thing? No human that I know of can, although I do know somebody who tried once. His name is Bart Netterfield. Hi, Bart, if you're watching this. He was a Bethel student here about 40 years ago. No, not 40, 35 years ago or so, with me. He was a physics major. He went on, he's relatively famous. He's actually got his own Wikipedia page. And he, evidently, the story goes, correct me if I'm wrong, went in a dark room one day and tried to visualize 4 dimensions. Spent hours in there, came out, said, wasn't successful. So you can't visualize it literally, but you can mathematically still work with it. And instead of a 3-dimensional hypersurface sitting inside 4-dimensional space, you also instead could think about, instead of level curves in 2-dimensional space, you could think about level surfaces in 3-dimensional space. Surfaces in 3-dimensional space, like the room we're in, on which the function is constant, could be thought of and could be even visualized and attempted to be drawn, maybe with technology, most likely with technology. Anyway, this is ultimately a Calculus 1 course, so to solve the problem, we will want to try to use constraints, perhaps, to simplify this to a 1-variable problem, a 1 independent variable problem. And we will be able to, because there are a couple constraints that will allow us to do that. So again, we've got the purchase cost, $22.46 times the number of cartons ordered per week. N was the number of cartons per order. $22.46. Let me write it this way: $22.46 per carton is probably the best way to think about the units of that. Times, I'll put an X for times. Again, number of cartons ordered per week, and as the number of cartons per order, how many cartons ordered per week based on that? It is N over T, yeah. N cartons per T weeks. Ultimately, the cartons units do cancel here, leaving you with the quantity that's in dollars per week. Yeah, that probably is what we want to use the units to be here. So that's the purchase cost. The delivery cost is $360. Times the number of deliveries per week. Go ahead. Yeah, that's true too. I did say that I'm not going to worry about that at the moment. Yeah, the truck can only hold 3,000 cartons and has to be less than 3,000, but I'm not going to worry about that at the moment. If T is the number of weeks between orders, pretend T is 2, for example, 1 over T would be the number of orders per week. If it's 2 weeks between orders, like you're getting half an order every week. Now, of course, you're not literally going to get half an order every week, but on average, that's what's going to average out to. 1 over T, the units would be, I guess you'd say weeks to the negative 1 power. So that the units of this are still dollars per week as well. So this is the purchase cost, this is the delivery cost, and then we add on the holding cost. 18 cents per carton per week times the average inventory between orders. 18 cents is $0.18. $0.18 per carton per week. Perhaps the best way to write the units there. Times the average holding cost or the average inventory between orders. Actually, the better way to write the units here is dollars per carton per week. Average holding cost is the I. No, it's the average inventory. I cartons. The cartons cancel. The units ultimately, again, simplify to dollars per week. Okay. So there is our initial formula for this function that we want to minimize. But again, it's a function of 3 variables. But we will not have to use multivariable calculus to solve the problem in the end, because we'll be able to get rid of 2 of the variables using some constraints. Before class on Friday, I'd encourage you to think about what the constraints would be. One of them is related to the usage rate that we use every week. And one of them is also related to this graph that you see. This one right here. See it there? That one. Right? Guess I should have done this. That graph. I forgot that I could do that. I would encourage you, if you want to get the most out of this, to think about what the constraints would be. And if you can think about them carefully enough, you can even solve the problem before Friday. You've got the tools to do it.